Hello, and I'd like to welcome you to Lecture 1.5, The Daily Path of the Sun. At the conclusion of this lecture, you're going to be able to describe the movement of the sun through the daytime sky. You're going to differentiate between a solar and sidereal day. You're also going to learn how to calculate the noon-sun angle and explain how this influences the seasons. And then last but not least, we're going to explain the reason for the seasons. So, without further ado, okay, on any given day, what you can see as the sun moves through our sky pretty much the same way as a star does. It's going to rise somewhere along the east and then, of course, reach its meridian, which is its highest point in the sky, which is, of course, right there in the center of this image. And then, of course, it's going to set in the west. Now, the question is whenever we start looking from the northern latitudes like we're at, you're going to notice that we are pretty much consistently going to look to the southern horizon to see the sun. That is a key thing that you want to focus on. It is, if you are above 23.5 degrees north latitude, you will always look south to see the sun. Okay, so here's what we're going to be looking at. What you're going to do is you're going to notice that throughout the course of a week, a month, and everything, you're going to notice that the sun is not quite the same as a star. What you're going to do is you're going to see the sun actually change its position in the sky. Okay, it's either going to be higher in the sky or lower in the sky, depending upon what time of year it takes. One thing that you have to know is that the sun takes a full 24 hours to make a complete circle around the celestial sphere, instead of the 23 hours and 56 minutes to revolve 360 degrees. So whenever you start looking at this, it's what we're going to try to explain, okay? And you're going to see coming up here how we explain the differences in those two times, okay? So whenever we define our day, of course, our day is based on the motion of the sun. All right, the first thing we're going to have to address those two time periods. You know, a 24-hour day, which is called a solar day. What this does is the solar day is the sun progresses from its highest point in the sky back to its highest point in the sky. So that is a 24-hour period. So over a 24-hour period, the sun is going to make and be back to its highest point in the sky. That is called a solar day. But whenever you start talking about a sidereal day, if you were to look outside of the Earth-Sun system and just basically use a reference star instead of our sun, what you're going to do is you're going to notice that the Earth takes 23 hours and 56 minutes for it to take one 360-degree rotation on its axis. Okay, so in other words, we have two types of days here. We have what is called a solar day, which is 24 hours, and a sidereal day, which is 23 hours and 56 minutes. Now the question is, why the difference? Well, it's our revolution. This is one of the most confusing things. So let me go ahead and get this set up here to where we can start marking on this so that you guys can see what's going on. All right, here we go. If I were to just take and say I'm going from this point back to that same point, what that is that's actually 23 hours and 56 minutes. That was a 360-degree circle. So if the Earth just rotated 360 degrees, that would be a sidereal day, and it takes 23 hours and 56 minutes. But if you want the sun to be at its highest point in the sky, which of course its highest point in the sky should be noon, that takes 24 hours. And the reason that it takes 24 hours is because, watch this, I'm going to start right here. I'm going to go around. And here's the problem. I went full 360 degrees, okay? But notice that the sun is not at its highest point in the sky. What I have to do is go that additional 4 minutes, that additional 1 degree before the sun is in its highest point in the sky. And that's all a result of our changing position, okay? So a sidereal day is basically 360 degrees, but a solar day, it takes additional time, and the reason that it takes additional time is because of the Earth's revolution around the sun. So we change our position, Okay, so that's what you're looking at there. That's the primary difference between those two. It's a difficult concept to understand. Once you start drawing it out and kind of use yourself as a model, you'll come to understand exactly what's going on. Okay? All right, next thing we need to look at is what is called the plane of the ecliptic. The plane of the ecliptic is this actual great circle that's on the celestial sphere that basically depicts the path of the sun. So what ends up happening is the sun follows this path. That is the plane of the ecliptic. Okay, now of course what causes that path of the sun? It really has nothing to do with the sun going around the earth. It has to do with the earth's rotation. Okay, now what ends up happening here is you're going to see that plane of the ecliptic, because of other earth's motions, is going to actually either decrease in altitude or increase in altitude depending upon which time of year it is. Okay, so this is what you're looking at. Whenever you start trying to understand the daily path of the sun, one thing that you've got to take into account is what time of year it is. Okay, if you're looking at June 21st, the summer plane of the ecliptic is exceptionally high in the sky. Okay, whenever we start getting to the equinoxes, notice that the ecliptic has decreased its altitude. So think of this as an angle. Okay, so there's that angle. There's that angle. So these angles are constantly decreasing as you progress throughout the year. Okay, so whenever you look at the altitude of the sun off of the horizon, so how high is it off the horizon? That depends on what time of year it is. And the question is, of course, why? Well, here's something you've got to look at first. This is another observation that we have to take. During December, whenever that sun actually sets, it's going to set to the west-southwest. So it's actually going to be more southwest than what is called due west. Okay? Whenever you're at the equinoxes, which are the spring and fall equinox, you're going to set due west. But during the summer, what ends up happening is you end up setting farther to the north. And again, that poses one of these questions. Why? Why does all this occur? Okay, so to help us explain it, the first thing you have to understand and you have to remember is that tilt. That tilt is constantly changing. Okay, or excuse me, it's not constantly changing. It's constantly pointing in one direction. Now in these diagrams, that's a little confusing, but here's what you have to look at. Whenever the sun is directly on the northern hemisphere, look at our tilt. Okay, so this is during our summer months. We're tilted towards the actual sun in the northern hemisphere. So what that means is that sun is actually at a higher angle. Okay, so it's going to be higher in the sky than it is during the winter months. Again, just focus on the northern hemisphere. Look how low that angle is. Okay, so it's closer to the horizon. So basically, the season determines when it's how high it is and how low it is. And of course, from this, you can probably start to notice that as you progress through from the summer to the fall to the winter, the altitude of the sun decreases. And that's all because of the tilt changing the sun angle. That's all it is. So that leads us into this. So what causes the seasons? Now, whenever you start looking at this, one of the most common misconceptions of what causes the seasons is distance. Everybody thinks that we are actually closer to the sun in the summer and farther from the sun in the winter. That's not true. We have two new terms here. We have perihelion and aphelion. Aphelion, anytime you see A in front of it and you see that word helio, it's not close. And of course, perihelion is close. So what we're noticing right now is if you were to look at this, you can see that we are 152 million miles away in the summer. But look at the angle of the sunlight. It's high in the sky. That right there indicates that's why we have warmer temperatures. look what happens here. Even though we're closer to the sun, it's low in the sky. So now the sun is what drives our seasons, and because we're getting a lower insolation, which is incoming solar radiation, okay, so insolation, because of that, that's why temperatures do not get very warm over here, and over here, because we get more direct sunlight, they are increased. That's what causes the seasons. And of course, you also have to take into account how much time are we exposed to the sun. Well, of course, during the spring and autumnal equinoxes, you can see every place gets 12 hours because the Earth is equally illuminated. But whenever you take the tilt and you're tilted away, up here is our winter, okay, so it's tilted, look at the time. You increase in the southern hemisphere, but let's just focus on the northern hemisphere. That makes it easier, okay? You notice as you go farther north, you have less hours of daylight. Less hours of daylight equals less time to heat things up. Whereas in the summer, more hours of daylight as you go farther north because the sun's rays are more direct, increased temperatures. That's why we have the seasons. Okay, so what causes this? The tilt of the Earth's axis is 23.5 degrees. It always points in the same direction, so of course it points, right now, all of these, it's kind of tough to draw on here, but they are all, it never changes. It always points to the star Polaris, okay? So whenever we're in this section of the orbit, or this portion of the orbit over here, you notice that the northern hemisphere is tilted away from the sun. So what that does, less direct solar radiation, the sun is lower in the sky, and temperatures are going to be cooler. Over here, in the summer solstice, the northern hemisphere is tilted towards the sun, more direct solar radiation, boom, you have higher temperatures. During the equinoxes, well, you see the key word in there, equal. They are equal. Each hemisphere is receiving equal amounts of sunlight. So that's why the seasons are always different in each hemisphere. Okay, so whenever you start looking at this, there's everything you need to know right there. So the reason for the seasons is basically the tilt of the Earth and our revolution around the sun. This is a great diagram that will show you exactly what's going on. Now the diagram here is focusing on the southern hemisphere, but it works exactly the same. Notice how right now the more direct sunlight is on the southern hemisphere, so of course it's in the summer. Okay, 6 months later, look at what happens. We're on the other side of the sun now. The northern hemisphere is basically tilted towards. This is just showing a comet there that does, almost all celestial bodies have that. Now the question is, as you see right there, what happens if we did have a perpendicular? What would happen if we had a perpendicular and not a 23.5 degree tilt? Okay, think of that question. All right, so here's what you're actually looking at. Whenever you start looking at this, on the first day of spring and sun, it crosses the celestial equator, okay? Well, whenever it starts to look at this, you're basically saying that what I have is I have a position right there, which is called the node, okay? So that's called the node. Well, whenever the sun is on the node, that's basically your equinoxes. And of course, you can see March 20th, March 30th at noon. And so what's happening to the altitude of the sun on March 20th, which is very close to the spring equinox, you have the sun right on the node, but then look up here. As you progress to March 30th, notice that the sun is higher in the sky. That's more direct solar radiation. So what does that mean? Temps are increasing. Okay, so whenever you start looking at this, this is basically putting it all together. What you can do is you can see these different paths of the sun. And what causes these different paths of the sun? Well, it's basically Earth's position in its orbit and the tilt of our Earth changing the direct solar radiation. So this is the next step. The last thing that you're going to have to be able to do is you're going to have to be able to tell me, okay, well, what is the angle of the noon sun? Okay, if the Earth were not tilted, this was a question I had earlier. What if the Earth had no tilt? Well, what that would do is that would actually limit your whole entire planet. First of all, your planet would have no seasons. It would actually have one. Okay, every location would only have one season if there were no tilt. So that's basically what you're looking at. But see this thing right here? That is the key thing. That is something called the analemma. Okay, so what we're going to do is we're going to look at, and I'm going to teach you now, how to determine the altitude of the noon sun. All right, whenever you start looking at this, first of all, you notice that you see this thing called the analemma. Okay, this is the path of the sun over the course of a year. Now, with this, all you see, notice over here, you see, of course, the equator. So that line is the equator. Here's what this tells you. The analemma, which is this figure 8 looking thing, tells you the exact location where the noon sun is directly overhead, or 90 degrees. So the noon sun would be directly overhead at these locations. Okay, so example, today's January 22nd. January 22nd is right there. So what we're going to do is we're going to go straight across. On January 22nd, the noon sun is directly overhead at 20.5 degrees. Sorry about the poor writing here. 20.5 degrees south latitude. So today, if it were noon and we were at 20.5 degrees south latitude, and I took you guys outside at noon and said, okay, I want everybody to look at the sun. Boom, it's noon. You would look straight up in the sky. So that's the position where the sun is directly overhead. That is a key thing. That's how you read this. So on April 17th, it is at 3 degrees north latitude. Notice that you have over here to the north, down here to the south. Okay, so that's what you're looking at there. Now, the next thing that you need to do, you have to use this analemma in this formula. Okay, please know this formula. The angle of the noon sun is equivalent to 90 minus the latitude of where you're observing from. Okay, plus or minus the latitude of the noon sun. This comes from the analemma. That's where the noon sun is directly overhead. So today we talked about that. That right there would be 20.5 degrees south. Here's the thing. Today, of course, I am in Springfield, Missouri, so 37 degrees north, 90 minus, and then in parentheses. Well, then you start to say we've got a big question right there. How do we know to add or subtract? Okay, an easy way to remember it is if the latitude and the latitude of the noon sun is in the same hemisphere, you subtract. Same, subtract. Well, you notice that here it's north, here it's south, so guess what we do? We add. So now, 90, let's go ahead and do it, minus 37 plus 20.5 is 57.5. Let me go ahead and erase this here real quick. Okay. Pin. And 37.20 is 57. Okay, that right there is 32.5 equals. Guess what that means? Today at noon, I would have gone outside, looked to the southern horizon, and I would have seen the angle of the noon sun off of that horizon being 32.5 degrees. Now, a question is how do I know that? How do I know that I would look to the southern horizon? Well, here's an easy way to do it. Whenever you start looking at this, I told you guys that we were at 37 degrees. So you would say, I'm going to look at the analemma, and I'm going to be up here, 37 degrees. Look at that. I've always got to look south to see the sun. The noon sun will never be overhead. Why? Because the noon sun has limits. 23.5 degrees north, Tropic of Cancer, 23.5 degrees south. Okay, so that's what you're looking at there. So that's how you determine what the angle of the noon sun is. You simply plug your stuff into this formula and it'll come out with the answer. And of course you got to look at which horizon. Okay, here's a perfect example. What is the angle of the noon sun for Springfield, Missouri on June 22nd? Let's go through it one more time. June 22nd, you can see I have the arrow pointing up here. That is 23.5 degrees. 90 minus 37, and notice this time, because look, they're in the same hemisphere, so you subtract them. 37 north minus 23.5 north equals 13.5. Look at that. How did that 76.5 degrees compare to that? Well, it's higher in the sky. Look at the date. That's our summer. This is our winter. There you go. The sun angle proves it all. Okay? All right. Angle of the noon sun for Springfield, Missouri on December 22nd. Now watch this one. Whenever you do this, 90 minus 37 plus or minus latitude of the noon sun. Here you go. Look at that. The math comes out 29.5 degrees. So now that we've progressed into January, 32.5. We've gone from the winter solstice to now we're starting to increase our height. So what are temperatures going to be doing? Increasing. Why? Because sunlight is more direct. Okay, let's progress on. Oops, I'm going backwards, sorry. All right, here's one more. Let's do this. Let's say today's date is December 22nd, and you are at the South Pole. Okay, here we go. The latitude of the noon sun, or the angle, is equal to 90 minus, and we're at the South Pole, so that is 90 degrees south plus or minus, and then December 22nd, let's go back to the Analemma. That's way down here. As you can see, that is 23.5 degrees north, or 23.5 degrees south. Okay. Whoa, look what's happening here. Same, you're going to subtract. Oops, 90 minus, that right there is 66.5 equals 23.5. So now here's the thing. Notice that I said I was at the South Pole. So guess what horizon I would look to? If I was at the South Pole, I'd look to the northern horizon to see that. Okay? Makes sense? That's how you calculate the noon sun angle. Now with this, here's the last thing. How does this actually apply? Well, what's really cool, if you've ever seen the movie Castaway, Tom Hanks actually uses the Analemma to help him get off the island. It's really neat how this can actually be used in multiple areas, because what he wanted to do is he wanted to look at getting the right time to, of course, get the winds to blow offshore. Well, of course, what drives those winds? Pressure differences, and of what drives those pressure differences? It's basically sunlight. So the more sun that there was, you change the wind patterns to be off the island. So just to kind of wrap that up. But it was really neat to actually see that, and I was like, wow, that's pretty cool, because I actually teach that stuff in class. So I hope this video has helped you with understanding the path of the sun across the night sky. You may go ahead and work on your lab activity now. And if you have any questions, you may contact me either via email or through the platform that we use for class. Thank you.